Now let's look at section 5.4. I think this is a pretty easy section. You probably could have just read it on your own, but here's a little video that goes through some of the theorems. Let's think back here on what our definitions are. We're looking at rectangles, squares, and trapezoids. And back from chapter 2, we have these definitions. Now, you could probably get away with less here. Okay, that these rectangle is a quadrilateral where all angles are right angles. Well, you could get away with a little bit less. You could say it's a quadrilateral with 3 right angles, and the fourth one automatically would be a right angle as well. But let's go with these definitions for right now. And here's let's do a few theorems here. This is number 526. Every rectangle is a parallelogram. Now, I'm not going to formally do this. We'll just make a sketch of the proof here. So here's a sketch. Okay. Okay, sketch of the proof. So let's assume that ABCD is a rectangle. Of course, that means all angles are right angles. In particular, we get that angle BAD. Well, we don't have to call it BAD. We can just call it angle A and angle B are right angles. Okay, so I've got a right angle here and a right angle there. Now I have other right angles as well, but all I need for right now is those two. Okay. So this means that BC is perpendicular to AB, and it also means that AD is perpendicular to AB. Now, if you go back and look at a corollary in a previous section here, in section, so corollary 5.2, I'm supposed to say corollary. Okay, then we know that BC is parallel to AB. Now, the corollary 5.2 said if you have figures in a plane here and 2 lines are perpendicular to the same line, then they're going to be parallel. That's, of course, it has to all occur in a plane, but quadrilaterals all occur in a single plane here. Okay, and by the same reasoning, okay, so BC and AD are parallel by the same, whoops, said this wrong here. BC and AD are parallel by the same reasoning. BA is parallel to CD. Okay, so rectangle is a parallelogram. Now, since that's a parallelogram, it satisfies all the parallelogram properties. So I won't write them all down here, but opposite sides will be parallel. We just proved that, okay? We have opposite sides must then be congruent. If you've got diagonals, it's a parallelogram, the diagonals bisect each other. So there's a lot of parallelogram properties that automatically now are satisfied by rectangles. Okay, again, we've got a few more theorems here, and I'm just going to kind of sketch through the proof here. This is theorem 5.27 that says if you have a parallelogram that's got 1 right angle, then it's a rectangle. So what we have here, because the arrows, we mean that AB is parallel to CD, and that BC is parallel to AD, and that we have a right angle at A. Okay, now, since this is a parallelogram, then the measure, well, we back up here. I don't even have to have parallelogram here. But since AB is parallel to CD, then angle A and angle B are supplementary. They are interior angles on the same side of the transversal when a transversal cuts parallel lines. Okay. So that means that if you add them up, you should get 180 degrees, and that's going to mean, since A is 90 degrees, so since A is 90 degrees and these things add up to 180, the measure of angle B has to be 90 degrees as well. The same sort of argument, once you have this, and these is a right angle as well, then I have parallel lines cut by a transversal. So the interior angles on the same side have to be supplementary. If this is 90, that has to be 90. And then just do it one more time here. Parallel lines cut by a transversal. Interior angles on the same side must be supplementary. This one's 90, so that one has to be 90. Okay. So the same reasoning shows that all of the angles have to be right angles. Okay, let's do a sketch of the proof from 528 here. The diagonals of a rectangle are congruent. Okay, so if ABCD is a rectangle, okay, then angle A and angle B are right angles. Okay, as shown. Okay, we'll not worry about C and D right now. So what this says is that I'm going to form some diagonals here. Okay. So angle A and angle B are right angles. So triangle BAD and triangle ABD are right triangles. Okay. Now, what do we know here? We know also that since ABCD is a rectangle, it's a parallelogram, so the opposite sides are parallel. I mean, opposite sides are congruent. So AD, side AD, is congruent to side BC. And since BA is congruent to AB, okay, in other words, this segment is congruent to itself. That's a reflexive property. Then we have by LL, you know, I have this leg is congruent to that leg. This leg is congruent to itself. Okay. Then I have the right triangle BAD is congruent to the right triangle ABC. And so these two triangles are congruent, so the corresponding parts, AC, which is the hypotenuse of one of the triangles, must be congruent to the hypotenuse of the other, BD. So the diagonals are congruent in that case. All right, this is a little bit longer one, and I'm going to do this one out, and it's done in the book as well, but I'm going to do this with two-column format, putting in all the details that we've just kind of glossed over on the previous ones. Okay, so if a parallelogram has congruent diagonals, then it's a rectangle. So what we're given here is that A, B, C, D is a parallelogram. Okay, and we're also given it with congruent diagonals, so that AC is congruent to, actually I want to write it a little differently here. Let's write it that BD is congruent to CA. Okay. And what we want to show is that ABCD is a rectangle. There's different ways of doing that. The definition of a rectangle means four right angles, but we've already shown if it's a parallelogram and we've only got one right angle, it's going to be a rectangle. Okay, so let's do statement. And reason. Okay, so one, we're going to write down all the given. Okay, it'd be nice to write it down where you can read it. And let's see, BD, diagonal, that diagonal is congruent to the diagonal CA. And that reason is a given. Okay. Statement number 2 here is going to be that AB and DC are congruent. So that this side and this side are the same length. And this is Corollary 515. If you're keeping track of numbers here, it says that the opposite sides of a parallelogram are congruent. Okay. Statement 3 I've got here is that AD is congruent to DA. So that guy's congruent to itself. And anytime you have something like x equals x, or something is congruent to itself or equal to itself, or other, that's a reflexive property. Okay, now we can do a little bit. Here is statement 4. We got a big conclusion here. Triangle ABD is congruent to triangle DCA. Let's make sure I've got things in the proper order here. A to B to D, D to C to A. Okay. And this is, the reason for this is BD and CA are congruent, AB and DC are congruent, and AD and D are congruent. This is by side, side, side. Okay. Okay, let's do some more statement and reason type of stuff up here. Now we're down to step 5. On step 5, we have the angle BAD is congruent to angle CDA. Okay, BAD is this angle, and CDA is that angle. Okay, and those are corresponding parts. Or CP, as the book writes it down here. So BAD and CDA are congruent angles of the two different triangles. That's the corresponding parts, and we're just about done now. Now, not only that they're corresponding parts, but they're supplementary. We used this before. This is corollary 518. Excuse me, corollary 5, 8, and that is when you have interior angles on the same side of a transversal. When a transversal cuts two parallel lines, interior angles on the same side are congruent. Oh, excuse me, supplementary. Now, congruent supplementary angles if these two angles have the same measure and they add up to 180 degrees, are right angles. Now, I'm going to go with the book here, but and they say because the reasons are 5 or 6. Actually, I think there should be several more lines written down here. Let's just say that congruent supplementary angles are right angles. Okay. And finally, for the last step, let's see, what do we got here? Oh, so these two guys, not only are they congruent, but they're actually, that's supposed to be a right angle symbol there and there. Well, all we need is one of these to be a right angle. Okay. And we have that ABCD is a rectangle by theorem 527. If you have a parallelogram with one right angle, then it's a rectangle. Okay, so not too bad, but it takes 8, probably ought to have about 10 steps in it if you put every single little detail in there. But when you write down a 2-column proof, lots of times you end up writing down a whole lot of stuff. Okay, here's an example. This is number 38, and this is page 277. We want to figure out the measures of angle 1 and angle 2. BCDE is a rectangle, so I've got right angles in the corners there. ABDE is a parallelogram. Okay. We're going to figure out the measure of angle 1 right here and the measure of angle 2. And we'll do them in that order. Okay, so let's see, ACD. So first let's look at this triangle. Oops, I need thicker lines here. That's too thick line. Let's look at this triangle. A to C to D. Okay, that's a right triangle. Okay, because BCDE is a rectangle. This is a right triangle. Okay, if this angle is 57 degrees, then the measure of angle CDA is 90 minus 57, which is 33 degrees. Okay, good enough? All right, let's keep this in mind too. CD and BE. Since this is a rectangle up here on top, it's also a parallelogram. So, excuse me, I back up. I need to write this in here. This whole angle here is 33 degrees. Okay. Now, if you look at CD and BE are parallel lines because BCDE is a rectangle, it's a parallelogram. So, and AD is a transversal. So it's transversal to CD, BE. Excuse me. Okay, so that means we have parallel lines cut by transversal, so alternate interior angles are congruent. So the measure of angle 1, back up here, angle 1 is congruent to angle CDA. So the measure of angle 1 is 33 degrees as well. Okay. Now let me get rid of some of this stuff because we haven't done parallelogram things yet. Okay. So there's angle 1. Now to get angle 2. And let's switch to a different color here. We're working on angle 2. We know that BD is parallel to AE. Right? Okay. So this guy is parallel to this guy. Oops. Okay. And that BE is transverse to those two things. Okay. So BE is transverse to these. So angle DBE is congruent to angle AEB. Okay, so this angle and this angle are congruent. So the measure of angle DBE is 18 degrees as well. So this is 18. Okay, just about done. Right. CD is parallel to BE. I've already said that. Okay, and in this case, CD, BE, DB is a transversal. Okay. So CD and BE are parallel. DB is a transversal of that. So alternate interior angles, CDB and angle EBD are congruent. That means that this angle here is 18 degrees as well. So the measure of angle CDB is 18 degrees. Okay, and finally we just look at what we've got here. We've got a big angle of 32, an angle of 18. So the measure of angle 2 is the 33 degrees for the bigger angle minus the 18 degrees is 15 degrees. Okay, typical sort of problem, doing some reasoning. You have problems like that on your long forms of your test, make sure you put in all the statements you can. Okay, let's talk a little bit about squares. If you go back to chapter 2, that very first slide I had here, a square is a quadrilateral with 4 congruent sides and 4 right angles. Now, I'm not going to say a whole lot, but since a square is a rectangle, because it's 4 right angles, then it's a parallelogram, so it has all sorts of parallelogram properties. It's also a rhombus, so it has all the rhombus properties. It's a rectangle, has all the rectangle properties. So if you want to know what a square is, you can use the definition, or these things are all equivalent. If you have a rectangle with perpendicular diagonals, it's a square. If you have a rhombus with congruent diagonals, it's a square. A rectangle with 2 adjacent sides congruent, it's a square. A rhombus with 1 right angle, well, that forces all, because a rhombus is a parallelogram. If it's got 1 right angle, it forces all of them to be right angles. Okay, so I'm not going to prove those. Those are all given in the little exercises in text, but they're just little 1 or 2 step proofs. Okay, now we have a definition, and I meant to put it in here. Okay, remember that a trapezoid, let's go back here. Got it here. A trapezoid is a quadrilateral where exactly 1 pair of sides is parallel. An isosceles trapezoid is a trapezoid where the non-parallel sides are congruent. Okay, so let's do some isosceles trapezoid stuff here. This is theorem 5.30. The base angles of an isosceles trapezoid are congruent here. All right, so again, this is just going to be a sketch of a proof here. It's done in the book as well. So A, B, C, D, oh, let's do blue. Don't want red. Is this blue now? Nope. Blue, please. Okay. All right, so A, B, C, D is going to be an isosceles trapezoid. So that means we're going to have AB is parallel to BC. And we're also going to have not AB, AD is parallel to BC. And we're also going to have AB congruent to CD. Okay, so this side and this side are congruent. Okay, now here's where we pull out something from the very first of this section, and that is the parallel postulate. Postulate 5.1. Given a line and a point not on the line, there is exactly one line containing the point that's parallel. So, by the parallel postulate, one says that there is exactly one line. Okay, let me see if I can write this a little better here. You can't read that. There's exactly one line through C parallel to AB. Okay. There it is. Let E be the point where this line intersects the line AD. So this is my point E here. Now it actually intersects the segment, but I don't know that E is between A and D. The way I've got it drawn it is, but it really doesn't matter. The line that's through C is going to intersect line AD in some point. We'll call it E. Okay, now let's see what we got here. Now what we formed here is A, B, C, E. We formed a quadrilateral. Okay, and we already knew that this, the base side AD and BC were parallel, but now we know that AB and CE are parallel, so ABCE so it's a parallelogram. So I got a whole bunch of nice parallelogram properties I can use. And one of the properties of parallelograms is opposite sides are congruent. Okay, so AB and CE are congruent. Well, let's look at what's going on over here on the right-hand side. This means since AB is congruent to CE and AB is congruent to CD, this means that CE is congruent to CD. So the triangle we formed over here, CED, is an isosceles triangle. Okay. So triangle CED over here is isosceles because those two sides are the same length. And since that's an isosceles triangle, the base angles are congruent. That is to say, angle C, I'll write this a little better here. Angle CED is congruent to angle CDE. So this angle, remember the angles opposite, when you've got an isosceles triangle, the angles opposite the congruent sides are congruent. Okay, well, we're just about done now. What do we know about angles BAE, BAD, which is the same as angle BAE, angle CED? Take a look here. What do we've got? We've got parallel lines BA and CE cut by a transversal. Angle BAE and CED are corresponding angles. When parallel lines are cut by a transversal, so they're parallel, they're corresponding angles for parallels cut by a transversal. So angle BAD, oops, is congruent to angle CED. But CED is congruent to CDE. So by what the transitive property here, And so angle BAD is congruent to angle CD, well, A. It's this angle here. CDE is the same thing as CDA. And we're done. This angle is congruent to this angle. Okay. Similar argument. Works at the top. So it would show that angle ABC is congruent to angle DCB. Okay, so base angles are congruent. Okay. Okay, so pretty straightforward there. You have to introduce this line, and the picture I've drawn here, the intersection point is in between A and D, but even if the intersection point, whoops, was, and you had to extend something, the proof would all be the same. Even if you had to extend one of these sides to get an intersection point, the proof would still work just fine. Okay, theorem 531 is a converse of this. If the base angles of the trapezoid are congruent, it's isosceles. Okay, I'm not going to prove that. It's actually pretty much the same proof, only backwards. Okay, you start with isosceles angles here, and you work your way back. It's pretty much the same proof. Okay, finally, I want to do one example of proof here. This is number 44, and it's a real simple little proof. The diagonals of an isosceles trapezoid are congruent. So we'll do this in a two-column format. So we're given that ABCD is an isosceles trapezoid. And so let's write down what we're assuming here about it is that AD is parallel to BC, so those are the parallel sides. And the isosceles bit is that AB is congruent to AB to DC, going up to the bottom. And what we want to prove is that AC, that diagonal is congruent to the other diagonal, DB. Okay, so do this. Ooh, wrong. Okay. So we have our statement and reason. Okay, and this is just, so it's pretty straightforward. I'm not even going to copy this down. This first thing is just given. Just write all this stuff in up here. Okay. So let's make a few marks here. AD is parallel to BC, and AB is congruent to CD, C to DC. Okay, 2, angle BAD is congruent to angle CDA. Okay. Previous theorem we had said the base angles of an isosceles trapezoid are congruent. So if I've got an isosceles trapezoid, okay, let me go back here. You can't read that. Okay. Angle BAD is congruent to angle CDA. because of base angles or an isosceles triangle are congruent. Theorem 530. Okay, now let's put some line segments in here. Okay, and for 3, triangle BAD is congruent to triangle CDA. Okay, so actually I need an extra step in here. I need a step 2.5. Let's get this down. What I did not say here is that AD and DA are the same length. Okay, and that's a reflexive property. Okay, so now I have sides that are congruent, angles that are congruent, and a side that are congruent. So BAD is congruent to CDA by side, angle side. And so the last thing is then that BD is congruent to CA, and this is corresponding parts. Okay, so that's section 5.4, and that should get you through the exercise. It's a pretty easy section to work with.